we are going to see the gate previous year questions on inter-process communication and synchronization. Okay. So let's move on to the question. Consider the following threads T1, T2, and T3 executing on a single process synchronized using three binary semaphore variables S1, S2, and S3 operated upon using standard wait and signal functions. The thread can be context switched in any order and at any time. So they have given the code for T1, T2, and T3 threads individually. And what they are asking, which initialization of the semaphores would print the sequence BCA, 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 and so on. So they are asking the value of S1, initial values of S1, S2, and S3, right? So this question was asked in GATE 2022 and it's an MCQ type question, right? So they are asking the values of S1, S2, and S3. So what is the sequence? It is BCA followed by BCA, right? So here, which thread prints B? T2, right? It prints B. Then which prints C? T1 prints C, right? And T3 prints A. Fine. So first I have to print B, right? So what they have given the code here. So this is an infinite loop. So all these are infinite loops because the sequence is infinite, right? So we have to keep infinite loops to print this sequence. So first I'll move on to thread 2 first. So I have to make S1. So for this to get activated, first I have to keep S1 as 1. So that this function wait of S1 makes S1 as 0. So you know, right? Wait function will decrease the value of the semaphore by 1. And the signal function will increase the value of semaphore by 1. Right? So this decreases by 1 and this increases the value of the semaphore by 1. So initially I have to keep S1 as 1. So wait of S1 makes S1 as 0. Okay. So here you see what happens if I keep S2 value also 1. Let's assume I keep S2 also 1. So when I keep S2 value 1, so see these T1, T2, 3 are the threads they can execute concurrently, right? So first what happens when I execute T3 first? If I keep S2 as 1, then A can be printed in the sequence first, right? So S2 should not be kept as 1. So S2 should be kept as 0. So when it is initially kept as 0, this wait of S2 will get blocked. Okay. Whenever S2 value becomes 1, it will move on to the next line. Till S2 value becomes 1, it waits here. Okay. Similarly, what happens if I keep the value of S3 as 1? If I keep S3 as 1, initially T1 thread can be executed and it can go inside and print C, right, in the sequence. To avoid that, I keep the value of S3 as 0. So the initial value of S1 must be 1, S2 must be 0, and S3 must be 0 to get the first three values of the sequence. So what happens to the rest we will see. So the initial value of S1 is 1, S2 is 0, and S3 is 0, right? So S1 first it will make it as 0, right? S1 will make it as 0 and print B. Then this signal, it signals S3, right? So signal will increment the semaphore value by 1. So S3 value will become 1. Okay, which code has S3, right? So T1 has thread 1 has S3 code. So what happens is, so next I will print which one it prints, T1 C, right? Before it's printing, it reduces the value of S3 to 0. So this one activates this one, okay, and this one activates this one, then this one activates this one, right? So first B is printed. After B, C will be, see here, see the following pattern. First B is printed. Okay. Then it follows this one. Then C is printed. Then again A is printed. After A is printed, it goes back again here. Again B is printed. Then again, see this arrow marks. So this is the initial point, right? From here, B is printed. Then C is printed. Then A is printed. Again, it goes back here. B is printed, C is printed, and A is printed, and it goes on. So the initial, they are asking the initial value of the semaphores only. So initial value of S1 is 1, S2 is 0, and S3 is 0. So let's see the options now. So among these four options, option C has S1 as 1, S2 as 0, and S3 as 0. Right? So this is the right answer. So this question was asked in GATE 2021 set 2 and it is an MSQ type. So let's see this problem. Consider a computer system with multiple shared resource type with one instance per resource type. Okay. Each instance can be owned by only one process at a time. Owning and freeing of resources are done by holding a global lock L. The following scheme is used to own a shared instance. Fine. So they have given this code. So this code says how to own a resource for a process. So what they are asking, which of the following choices about the above scheme is all right? So they have given four options. Okay. So this scheme ensures that deadlock will not occur. So let's check whether this scheme ensures deadlock or not. Okay, fine. So they have given, okay, so what they have given, first the function acquires the lock. Okay. Then if the resource is available, then I can acquire the resource and use it and release the lock. Else, if the resource, that means the resource is not available, that if the resource R is owned by another process P, then terminate that process after releasing all the resource owned by P, then you can acquire the lock, then restart the P, then release the lock and end if, okay, fine. So they are asking whether this code ensures deadlock or not, right? Fine. So let's assume the process P1, okay, P2. And there is a process P is which is already available, which is holding the resource R. So let's say P1 is acquiring the lock. Okay, now the lock is with P1. Okay, then R is available. No, the R is not available, right? With the R is held by process P. So P1 cannot acquire this resource. So it goes to else part. If R is owned by the process P, yes, the R is owned by process P, then I will terminate the process. First, I will release this resource and then terminate this process. Okay, then P1 can acquire this resource. After acquiring the resource, P1 can perform its own task. Okay, then restart P, right? So wherever P has stopped, it has to get restarted after completing P1. So again, P1 can acquire resource R, right? So then this lock is released. Then whichever process wants can acquire the lock. So there is no condition of deadlock. This scheme ensures deadlock will not occur. Option A is right. Then this scheme may lead to live lock. So what is a live lock? So it is similar to deadlock, but the states of the process might be get changing, but no effective utilization is done, but the states of the process might be get changing. In deadlock, the process states will not get changed, whereas in live lock, the process states might get changed. So here there is a process P and Q. Process P1 holds resource R1. Process P2 holds resource R2. Okay, then process P requests for R2, then process Q requests for R1. So this is the deadlock, right? Here no state changes will be there. So, but in this code, see here, terminate P and restart P, right? So from currently executing state, it might go to the ready state or blocked state, and again it can restart, right? So there is a chance for a live lock in this case. No deadlock, but there can be a chance of live lock. Fine. So let's move on to the next option, C. This scheme may lead to starvation. Yes, if there are more number of processes. So here option A is right. Already we have seen option B is right. Now let's see option C, right? So if a process acquires a lock, fine, and then already a resource, process P holds a resource R which gets preempted. A new process, let's say P1, after acquiring the lock, gets hold of this resource and does its process. Then I have to restart P, right? P is restarted. Again, if a new process comes, again I have to preempt this one, right? And then I have to get hold of this resource, right? Again, I have to restart P. If again a new process comes, again I have to get this, I have to preempt it first, and then I'll get hold of this resource, and so on, right? So here P, the process P can get starved. So there is a chance for starvation also. So this scheme violates the mutual exclusion property. Since there is a lock variable, it guarantees a mutual exclusion, right? Only one process can be accessed in the critical section at a point of time. So that is mutual exclusion. Since there is a lock available, this scheme does not violate any mutual exclusion. It guarantees mutual exclusion, this code. Since there is a lock, only one process can get inside and then can acquire the resource, and then it can release the lock. No two processes can have the same resources to get proceeded, right? So it guarantees mutual exclusion. The scheme violates mutual exclusion is not the right option. So A, B, and C is the right option here.